Hello and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy, and in this video, we'll be discussing discrete probability distributions and their expected values. Game theory involves, at various points, considering some amount of uncertainty, which requires the use of probability. Bottom line up front, if you see something in this video that seems terminally weird, don't worry. It's probably a bit of mathematical formalism sneaking in, and we'll provide some examples and ultimately not need the formalism for its own sake. Here's the longer version, which begins with a little story about math. In the 19th century, math experienced something of a dark night of the soul when it realized that it wasn't sure whether the real numbers actually existed. Math had been humming along just fine under the assumption that the real numbers existed. But then, people began to realize that they needed to prove that the real numbers existed. If the real numbers didn't exist, then math, as everyone knew it, would be significantly incorrect, which would be a very serious crisis indeed. Fortunately for math, it turned out that the real numbers do exist, and math continued on its merry way. One of the side effects of this whole episode is that modern probability requires some very formal mathematical machinery to avoid some very pathological formal math demons. We will studiously avoid the pathological formal math demons, but in the interest of being correct, some of the formalism will make short cameos in this video about discrete random variables, and the next video about continuous random variables. Like we said at the beginning, we'll ultimately provide examples and not worry so much about the formalism. First, we'll define discrete random variables and their sample spaces. A random variable is one which takes as its value the outcome of a random event. Prior to the occurrence of the random event, we know that the random variable will take one of several possible values. After the occurrence of the random event, we know which value the random variable takes. As it turns out, you probably already have a lot of experience with random variables. The outcome of a coin flip and the outcome of the roll of a die are both random variables. Birth month is another example of a random variable, although we don't typically think of it as such. You should take a moment to come up with some other examples of random variables. Examples are how we gain deeper understanding of definitions, theorems, and so on. As we go on through our course, if and when you encounter something new, or something you want to understand better, you should immediately start making examples. If we have an example of an x, that example allows us to answer quickly questions like, does an x exist? If we want to know whether y is always true, and we have many examples of y, we might begin to try to prove that y is always true. If, on the other hand, we construct an example of y is false, we can know quickly that y is not always true and abandon our proof attempt. Another math story, perhaps more of a math legend, about the role of examples. The cult of Pythagoras held as a tenet of faith, all numbers are rational. Some poor cult member up and proved that the square root of 2 is an example of an irrational number. Instead of celebrating this breakthrough discovery, they promptly drowned the poor guy for heresy. If a random variable is one that takes as its value the outcome of a random event, we want to know what values it could possibly take. We call the set of possible outcomes the sample space. The sample spaces associated to the random variables listed above are heads, tails, 1, 2, 3, 4, 5, 6, and January through December, respectively. This video is about discrete random variables, so let's say what it means to be discrete. It means that the sample space is countable. For our purposes, countable means finite. A sample space is discrete if it is finite, and a random variable is discrete if its underlying sample space is discrete. All of the sample spaces listed above, and therefore all of the random variables listed above, are discrete. We haven't actually talked about probability yet, so let's do that now. We associate a probability mass function to each discrete random variable. The probability mass function tells us the probability that a random variable takes on a particular value. Continuing our examples, here are the probability mass functions associated to the coin, the die, and birth month. Note that only now have we specified that the coin and the die are fair. Note also that a random variable doesn't need to assign the same probability to each outcome in the sample space. People are not evenly distributed by birth month, even adjusting for the fact that months have a different number of days. The probability mass function has two very important properties, outlined in this lemma. First, the probability mass function takes values in the 0 to 1 interval. Second, summing the probability mass function over the sample space is equal to 1. You should take a stab at proving the first using the fact that probability is a number in the 0-1 interval. You should take a stab at proving the second using the observation that the sum represents the probability that the random variable takes a value in the sample space. The last thing we need to discuss is the expected value of a discrete random variable. Expected value is a weighted average, using the probability mass function as the weighting function. Expected value really makes sense only for a random variable that takes on numerical values. Let's compute the expected value of a standard die. The sample space is the set 1, 2, 3, 4, 5, 6. Let's expand the sum. Each term of the sum is the product of an outcome and the probability that outcome occurs. Since the die is fair, f of 1, f of 2, and so on are all equal to 1/6. A bit of arithmetic, and we see that the expected value of the die is 7/2. Sometimes you will hear people describe this number as the average rule, an equally correct description. Here's a practice problem that pulls everything together. In this description are the sample space and probability mass function associated to a discrete random variable. You need to identify each of these to compute the expected value of my speeding ticket. Pause the video for a few moments to try the problem, and when you are done, unpause it to see the solution. The sample space is the set of possible speeding ticket costs, namely 0 and $2.90. Now, expand the sum. The probability of no ticket is 2/3, and the probability of a $290 ticket is 1/3. The expected ticket cost is $290 over 3, which is 96 2/3 dollars. Thanks so much for watching this video about discrete probability distributions.